Nothing will be outside what's being taught. Yeah. Now, today what I will do, today we will cover certain things which are bit complex in the sense that this can't be done by hand calculations. But what I will show you the models, right, and how they can be used, and these are good from the point of view of when you are doing a real design. So you will do these things using softwares. Okay, you will do using these things using softwares. So the question is that what to use and how to use it. No, some are unstable. You get all or how many more? Yeah, but you basically put a bunch together. You take one. How many two is it? One unstable. Okay, so what I will do, I will cover those things. So these are for your understanding. They won't be examined, right? And there's another section for down improvement. Again, there's a down improvement. Right? And there are sort of last topics. Okay? But these won't be examined. So these are just for knowledge and understanding. Those who will do a MSc project will be using these things as a part of their,
These from the
yeah. Oh, right. So yeah, that's a good thing. When the initial part, Is there any question? Yes. Oh. Any missed you? Yeah? Oh. Other one? Is there a question on the course so far? No? Are the contents, is it loaded too much or is it just right? In terms of the overall content, is it too much or it is too little or light amount compared to other modules?
I would say it's maybe it's not defined in terms of which one we would be questioned within the exams.
Now, what I mean to say, the as a whole, the whole course,
Yeah.
what I am covering, is it too much compared to other modules or it is higher or bit moderate? What bit more than the other. Okay. And is the coursework too much, or is the coursework is bit in terms of the credit is it a bit high? What is it? Fine.
The amount of work, I think it was a low percentage.
So for a 20% credit,
Yeah.
so it is a bit high in terms of.
Yeah.
No. Anything no can now some yes and no. Okay. Yeah. No, but if somebody is taking out of discipline, a little bit of more, so they have to do the background action now, or they will be a bit more. For those who already sort of understand various things, they find it. So obviously, look at the average thing. What about you? You find it a bit more time consuming compared to other courseworks, or is it okay? Yeah. Yes. Yes. Should I use the code to access my Google account in Philippines? 787 424. The security on that. You got the notes? You got the notes? Okay, so whatever we have done so far is the vertical load, yeah? So vertical load means, so if you know the vertical load, what your pile must take, so once you know your pile dimension, the diameter, the length, is an open-ended pile or a closed-ended pile, so a solid pile or a hollow pile, you can work on capacity, right? However, so that is the vertical load. That means if you design as vertical load, that means the pile will not settle, right? The pile will not settle, there will be no failure in terms of bearing. However, another thing is lateral load. So often piles do carry lateral load, right? Say, can you give me some examples of lateral load in piles?
Wind turbine.
Wind turbine is a big lateral load, a moment. Anything other than that? Apart from wind turbine, yeah?
Waves, wind.
Waves, wind, yeah? In a normal building, you have wind load. So if you have a very tall building, there's a wind load. Who takes those lateral loads?
Foundation.
So the foundation. So say you have put a very tall building. So that's a down level. You have a very tall building, right? And you have the foundations there, right? And the wind will be like that, right? So you know the wind speed, you know the wind speed, you can find out the thrust, right? And when you know the thrust, you get a lateral load acting on it, right? So who will take a lateral load? So this is applying a big load there, right? So these piles will take these loads, isn't it? Yeah. So there will be a reaction. So somebody has to resist the lateral load, otherwise it will move. Yeah. Right. From wind speed, you can work out the pressure. It is, because what happens? Well, not time. Basically, if you think about a flat, yeah. So if you have a flow, so there is momentum, mass and velocity. So some of the wind is going at say 10 per second, and as the wind pushes it, so it stopped. So the momentum is becoming zero. So from change of momentum is force. So you can get back the thrust. Roughly 0.6 v squared. It's thumb rule, but of course there are codes of practice you can get exactly. Once you know the wind speed, you can work out the pressure. Once you know the pressure, you know the area, you get the force. Once you know the force, that force has to be resisted by the piles, and you can work out the lateral loads, right? Okay. Other examples of lateral loads. Earthquake is big lateral load. Earthquake is the whole building shakes at 0.2 g, 0.3 g, 0.4 g, 0.4 times the gravity. So you know the building mass, that inertia is big lateral load. Any other example?
Soil movement. Soil movement.
Okay. If there is a small movement there, you'll apply lateral load there. Right? Any other example? Because many of you will work on different projects. Say for example, jetty structure. If you are building a port, right? So if you have a port, you're building a port, that will be a vehicle impact. The vessels can come and impact, right? So again, the vessel, though you slow down, it can come and give a big impact then, right? Once you move something, they'll give you a snatch load, right? So lateral loads are inevitable. And if you have lateral loads, then there's a tendency to put piles. If there's a lateral load is quite high or medium to high, there's a tendency that you have to go for pile for our long-term sustainable solutions, right? Okay, so how do you take into account in the design? What are the things you must consider? Yeah.
Shear, bending.
Shear bending, yeah. So basically, let's now have the problem that you have got a pile here, right? And that's the soil, and you have a lateral load there, right? So think of this. You have got in one case a pile which is short and stubby. In another case, you have got a pile which is long and slender. Will they behave similarly or behave differently? In what ways?
The short one will be more rigid.
Okay, so short one will be more rigid.
So probably be more rotational, whereas the longer one will have more flexion.
Yes. So if I want to tell in technically, in what it means that in this case, when a pile, okay, what do you mean by pile failing? Lateral load. Pile failing means anything what fails means. So you keep on applying load. At a certain point, a small change in load will give a big change in displacement. That's by definition a failure. So if you apply a load, you get displacement. At more load, more displacement. More load, more displacement. Proportional. But you will see a certain point, a small change in load, big movement. That's a failure. Do you agree? Yeah? So, if you assume that definition, both of these piles will fail. In this case, when it fails, the soil would fail, the pile will not fail. The pile would be sort of undamaged. For a rigid pile, if it fails, the pile will not fail by plastic hinging or no yielding. the soil would fail. The soil, so you pushed it too much that the soil around it has yielded. So it went to its yield strength, right? This case, the pile will not fail. The pile would fail as a whole, but pile as a member, like a beam, will not have an hinge formation. Yeah? So what I mean to say is that you will see a pile failing means it fails like that, right? Yeah? But if you have a long pile, if you have a long pile, you will see that it forms a, you will see that it formed a kink there and fell like that. So here the plastic hinge form, right? So in a short pile case, the soil fails. And in a long pile case, the pile yields. Right? In this case, what do you calculate? Yes, so you will calculate the moment applied by the load, and you will compare with plastic capacity, MP. Right? This is what I mean. Like in these sort of long pile cases, as you apply the load, the pile would have a bending, it will start to bend. As it bends, there will be strain forming, and if the movement increases to a limit, it will form a plastic hinge. Right? So you will calculate the bending moment and compare with the yield moment, how much that thing can take. In this case, the soil may not fail. All the soil may not fail. The soil may be still within its workable range. But for this case, the soil around would fail, right? That's the two main definitions. So how do you differentiate a rigid pile and a flexible pile? Yeah? Okay? Okay. So that's sort of a premise of this lecture. And okay, so this is what we have done, right? And that's the exam question, sort of how we calculate these things. Yeah? That's basically the vertical capacity of the pile, right? Okay, so that's what I'm now repeating here. Now in terms of lateral load, we often do a approach like this. So if you see in most engineering practice, what they will do, what will be done is effectively you will model the pile. Suppose it is done by somebody doing structural engineering. So they would act out a model like this. They will ask geotechnical engineers, give me pile stiffness springs. What it means? That means, what is the vertical spring? That means if you have a pile in the ground, I must know what is the spring constant, like Hooke's spring, right? So what load, what is the displacement? Yeah? That is a vertical. Another spring will be lateral spring. So at what lateral load, what will be the pile displacement? So this unit will be kilonewton per meter. So how much load you need for 1 meter displacement. Analyze the rocking spring, that would be meter per radian. For 1 radian of rotation, how much movement you would need, right? So this model is a model preferred by those who do structural engineering, because then they don't have to worry about all the soil part there, right? On the other hand, another model is you do the whole thing together. You hold the whole thing together and you model the pile by a series of discrete springs at different depths. And this is known as Winkler springs or PY method. PY, TZ, QZ method, which I will explain in the class today, right? Okay, so in terms of your calculations, I get 3 methods. Okay, One is a hand calculation method, which is will take you 10 minutes. You simply sit down and just do it by hand. You do it very quickly. And another is this standard method. It will take you 2 hours, couple of hours. So there are many softwares like to do all this thing like Alp, EY, GN. Many will use Alpine. There are quite a bit of software, not very expensive, £1,000 it costs. A company can afford to buy one off, and then they can run this analysis. An advanced method is where you use finite element software with advanced constitutive model of soil, and you need a very dedicated person who can run all this thing. Now, this is almost never done unless you go to litigation case, unless you go to litigation level, big claims, like a few million pounds of claim, right? For certain issues, then you go and say, do all these things. Because you cannot afford to run analysis for simple problems, right? If it's very important construction, very important building, very important like nuclear power plant, you will go for that method. In most cases, they will use this method. Any consulting firm, this sort of method, which is the pure method. And typically contractors will use this method. Contractors don't want to invest more on their design time. They want to simplify the way to do it. Right? Safe method, safe. Okay? So there are three main methods. Right. What I was showing you before is that is the two types of failure. So if you see a short rigid pipe, the soil fails. In another case, long flexible, the pipe doesn't fail, it forms a plastic hinge, right? And there are ways to calculate all these things. There are many simplified equations, right? So but how do you know which one would go on, right? Any idea what would be that function of? Say for example, somebody gave you a series of pile lengths and diameter and the ground profile, and ask you, can you tell me which one would, what is the behavior? Any idea?
Stiffness.
Stiffness of what?
Like
Of the pile.
yeah.
Okay, so that means suppose I'm taking I'm taking this ground soil in Guildford clay. Yeah, it's clay. It's clay. So I give you a concrete pipe, steel pipe, aluminium pipe, brass pipe, plastic pipe. Can you tell which one would be rigid, which one would be flexible? With the REI, is it adequate? So the question is that in Guildford, I'm giving a series of plastic in HDP pipes, some aluminium pipes, steel, concrete, and I'll tell you, I'll give you the lengths. Can you tell me whether it will behave like that way or that way? Okay, so let me start with a simple way to explain what I mean to say. Say for example, I have this pipe and this pipe, yeah? So assume that's a rigid, right? If I dip them in a thick yogurt, how will they both behave? I dip them in a yogurt, right? Yogurt pot, and I'm giving a movement. Yogurt is with milk you can.
Yeah, yogurt will fail on the pipe.
Right. Okay? Now, I put them both in a dense sand. I will use your thing, fill it with sand, fully. Yeah, I fill it with sand. And I put this and I push it. And I put them push it. Or I can take a really thin needle, like thin needle, like I think I can take one of your rulers here, right? They are very, isn't it? Flexible, isn't it? How will it behave? I dip it there, and I give a push. Will that bend? Will this bend? So what is the function of? Now, ratio of two things, isn't it? Yeah. So that is known as relative pile soil stiffness. It is a function of. It is not a function of two things. Isn't it? So how is a pile stiff? How much stiff compared to the soil around it? Yeah. So you will see it's a function of pile stiffness by soil stiffness. Right? So there are some correlations which you can use to say you can predict this will behave like a rigid pipe, like a flexible pipe. Okay? Right? Remind me, I will give you a last handout. These are correlations in one page or one so it will be quite helpful for your practice. No? So can somebody take a note and email me these things? So if I give, so basically what you do, so to predict what you will use to calculate, obviously there are different things in it, two different calculations. So if you know that ratio, pile to soil stiffness ratio, you can then say it will behave more like rigid or more like flexible. There is some in the borderline as well, so it's quite hard to say. Okay. Another important part is L by D, length by diameter. So you can differentiate the behavior by these two parameters. Yeah. Now tell me, if you want to find out the capacity of these piles, what do you think will go among those two groups? L by D. So if you look into the equations, so once you know your pile dimension and the soil around it, you can predict will rigid pipe or flexible pipe, right? Yeah. And then once you want to do some calculations, rigid pipe behavior will be mostly governed by this aspect ratio. Okay. And this will be governed by pile soil stiffness. If you look at the equations in course of practices, those things are tied down. So if you see an equation, you have this term, P over S, then you can say actually that means it is a flexible pile formula. That behave in a more flexible way. And if you see the formula has got L by D, it's a rigid formulation, right? Okay, now what happens? Now these are this is to see and you can guess what to use, you know, and you can find out if somebody has done it correctly or not, because actually they did it correctly. Okay. Now, what I would say other than that. Okay, that's fine. This is now to do those rigid behavior. What happens in reality? You will see as a rigid pipe tries to rotate, a wedge forms the top. Right now, you can see a wedge forming, right? And as you go down, as you push, the soil wants to move around it. If you take a very long pipe and you push it, the soil will there will be gap forming, it will yield like a wedge. As you go deeper and deeper, the soil wants to flow around it. What's happening at that level? At that level, what happens? Say at that level, here, yeah. So the pile wants to move laterally. So it was here, and it wants to move somewhere there, right? it has to have this soil displacement. The soil has to move, has to give way for it to move. So the soil will start to flow around it. Okay, it's like a fluid mechanics, isn't it? So you have a flow around it. So these mechanisms govern, right? And at the base there is some shear as well. So if you see, to do this sort of calculations, what you do, you can assume a pressure distribution. So you know the applied force and you know the pressure distribution. You assume something, and from there you can work out the maximum moment. Yeah, I think you've done it, sir. You've done it in Bloom's method. Yeah, so you have a shear, like a sheet pile design, similar thing. You assume a pressure distribution, and then you work out the shear force 0. Shear force 0 is maximum moment, and you can work out the moments. Yeah, so you assume a pressure distribution. As it moves, so it's pushing the soil, they'll be active, passive. So you assume a distribution, and you can from there you can work out the point of 0 shear, and the point of 0 shear is the location of maximum moment. You can calculate by a simple beam theory, whatever belongs in equilibrium, right? Right? So that's the thing that happens. However, these are checks, so you can do a quick check, you can have, but when you submit a calculation to a client, you normally do this Winkler method or PY method, right? So in a PY method, have you ever done PY method? Any of you? Any of you? No? So I'll take it very patiently then. In a PY method, which is known as the Winkler method, Winkler spin approach, what we are doing, we are assuming that that's a pile, a lateral load and a moment. So when you apply the load, who is resisting it? The soil. Who will give you the resistance? This soil, isn't it? This soil. So what we are trying to say, let us assume that the pile is like a series of elements, beam elements, right? So what we are saying, let's assume that it is a series of beam elements. Okay? Right? Now, when you apply any lateral load at the top, the pile would deflect, won't it? So as the pile deflects, so let's assume a shape of deflection chain. That's center line. So it will have a higher at the top. As you go down, it would reduce. So this element is now here, right? This element is now here, right? And we make it so small elements that, so now we say that this element moves laterally, sideways. Yeah, it moves sideways. So let's represent this interaction by one spring. Okay? Because if I assume that, ignore this rotation, I can assume very small elements. So I can assume that this is an even more small element. This is one element. I can make it even more small, right? So what I will see that this element was initially there, and it basically moved from here to there, right? So it now became like that, right? So there is series of all these elements, and each element moves sideways, right? And we represent this by a spring called P Y spring, right? So I can make it every half a meter. I can make. So I'm assuming that it's a series of like elements, right? And each has got a spring attached to it. Yeah. So what does this spring represent? So the model now becomes, and that is K1, isn't it? K or Py spring. Now, what it is doing, these springs are known as Py springs, and what they are doing, they are trying to capture the pile soil behavior. So pile soil interaction. Agree, right? So the pile is moving sideways, right? The pile is pushing sideways. Yeah? Now, so that's the whole model. So the model is that you are modeling a pile as a beam. Why it's a beam? Because the axis is in that direction and the load applied transverse. So beam is when you apply the load in other directions, not in particular direction. So in this model, we model the pile as a beam, laterally loaded beam, The beam is loaded laterally by load. It is supported on many springs. They are the Py springs. They are springs, right? And so therefore these springs must represent the beam.